Good morning, children. Today we'll talk about mutual induction. As you all know that yesterday we had talked about self-induction, that is production of induced EMF in the same coil. Now we'll have two coils side by side like this. And what we are going to do now is, we are going to produce current in one circuit and EMF will be induced in another circuit. So let us consider a source of EMF being connected to one of the coil. This coil will call as P coil, that is the primary coil, generally known as primary coil. This will be treated as a secondary coil and will denote it by S. To check the change in current in primary coil, how it is affecting the secondary coil, we'll connect a galvanometer in the secondary coil. And as you already know that as soon as the current will start growing in the first circuit, if I close the switch, the current will increase from 0 to I. Magnetic field produced due to the current in primary coil will increase. A nearby coil is now under the effect of changing magnetic field produced here, and therefore a small current depending upon the number of turns will get induced in the secondary coil, which will be detected by galvanometer. You can also do the experiment the other way around. Now you can disconnect this key. Now current will decrease from I to 0. The induction now will be for decreasing EMF, and therefore now the current will induce in a different direction. Now as we did for self-induction, the derivation will be exactly in the same manner. Now the only difference being is that the magnetic flux is linked with the second coil because of the current in the first coil. There we had both the variables in the same coil. So phi 2 1, that is the magnetic flux induced in the secondary coil due to the first. You can also use S and P. You can also use 1 and 2 here, depending upon whichever book you are using. So these are same things. In some books you won't get 2 and 1. It will be simply for the two coils. So all of them are same. Phi to 1 is found out to be proportional to the current in the first circuit. And when you remove the proportionality sign, we'll get a constant. Now instead of L, we'll have M, and this M is a constant known as coefficient of mutual induction. Coefficient of mutual induction or mutual inductance. These are the same things. Coefficient of mutual induction or mutual inductance. Now see the factors on which this M will depend. As you already know that L, which was coefficient of self-induction, was dependent upon number of turns, area of cross-section or cross-sectional area of the coil, and also on the permeability of the material of the material on which the coil was wound. One more factor which will be introduced here is the relative orientation of the two coils. These 3 points are same. This fourth one is different, that is the relative orientation of the two coils. See, when we say relative orientation, I'll tell you one or two orientations. See, one which we have already drawn. Another is you can have coils side by side like this. Another is you can have coil S like this. So in either of the cases, the induced EMF will become different, and you can say that the maximum induced current will be in the case when one coil is wound over the other like this. In this case, maximum induced EMF will be C. Now we'll go for from the same expression to the expression of induced EMF. How much EMF will be induced? So we'll again use the same formula. E is equals to minus d phi by dt. This we have already done. So in place of phi, now I'll write down this minus d m I1 upon dt. So induced EMF will be equal to minus m di by dt. Definition of M from exactly in the same manner as we did for L, from the same expression. Mutual inductance is equal to the induced EMF when the current through the primary coil is unity or 1 ampere. If you want to define from this expression, mutual inductance of two coils is numerically equal to the induced EMF when the rate of change of current is unity. As far as the unit is concerned, unit is also same, Henry. Now we'll find out the mutual inductance of two long solenoids. Mutual inductance of two long solenoids. Now we'll consider the case of maximum induced EMF, and we'll consider two coils again, the primary and the secondary coil, which are wound over each other. Let a current I flow through the primary coil, and let the cross-sectional area of the primary coil be A. Now we'll again start from the same expression and exactly in the same manner what we did yesterday for the self-inductance. See, the initial formula which we already have for mutual induction is M21I1. This will be our equation number 1. Now phi 21 will also be equal to the magnetic field because of the first coil, the area of cross section, and the number of turns in the first coil. You remember it is magnetic field B1 is mu naught N I1. If the number of turns is N1, it will be mu naught N1 I1. And what is phi? B into A. So phi 21 will be equal to B1 into A, and in place of B1 I will write down mu naught N1 I1 multiplied by A. Now this is N1 is number of turns per unit length of the first coil. If N2 is the number of turns per unit length for the second coil and the length of the solenoid is say L, then in that case total turns is equals to N2 multiplied by L. So total flux, now again denoted by capital Phi like this. This was the flux associated with a single turn. Now this will be for all the turns. So phi 2 1 will be equal to mu naught N1 I1 A multiplied by N2 L. This is going to give me mu naught N1 N2 A L and then I1. This is my equation number 2. Now compare equation 1 and 2. Comparing equation 1 and 2, you will get M2 1 is equals to mu naught N1 N2 A L. And you can just see the only difference being between L and M is there you had N square, and now here you see that the number of turns of the two coils are also introduced. For both of them we have different number of turns, and therefore both the number of turns has appeared in the formula. Now exactly in the same manner you can find out M12, which you will see that will come out to be the same. The only difference being initially you will have N2 here and later on you will have N1. So M12 will also be found out equals to mu1 N1 N2 AL, and therefore you can say M12 is equals to M21 is equals to say M, where M will be now equal to mu naught N1 N2 AL. This is the expression for mutual inductance of two long solenoids. We'll be doing the energy stored in the inductor tomorrow, and then we'll talk about AC generator. This is for today. Thank you.